Good day, beautiful people. I welcome you again to Physics 108 class. And this is our third experiment for the semester. I'm so excited that we are moving gradually. And today we'll be taking determination of the specific heat capacity of a liquid by an electrical heating method. Determination of the specific heat capacity of a liquid. You have to underline specific heat capacity there. By an electrical heating method. Now the first thing we'll take into consideration here is introduction, followed by the objective of the experiment, the apparatus we'll be needing for this particular experiment, the method or procedure to follow in getting what we need in this particular experiment, our data or result presentation, our graph, our slope, and the precautions to follow during the course of this particular experiment. So moving on straight to the introduction, I have specific heat capacity. That is one of the keywords in the title, in the experimental title. So it says the specific heat capacity of a substance is the amount of heat that must be added to 1 unit of mass of the substance in order to cause an increase of 1 unit in temperature. Now in simple terms, what this means is that specific heat capacity is the amount of energy that is being required to raise the temperature of a material, the temperature of one unit mass of material. You know that unit of mass is in kilogram. So let's say the temperature required to raise the temperature of 1 kilogram of material by 1 degree Kelvin or Celsius. And remember that our temperature is in degrees Celsius or in Kelvin. So a specific heat capacity can simply be said to be the amount of energy. Remember, energy, heat energy now in this particular instance. The amount of energy required to raise the temperature of 1 kilogram of material by 1 degree temperature. For liquid at room temperature and pressure, the value of the specific heat capacity according to experiment is approximately equal to 4.2 joule per gram degree Celsius. This implies that it takes 4.2 joules of energy to raise 1 gram of water by 1 degree Celsius. So in some instances, that joule that gram can be converted to kilogram. So by the time you are converting to kilogram, you'll be having 4,200. Excuse me. So in some instances, you might not see the value of the specific heat capacity of liquid at room temperature and pressure to be 4.2. You might be given 4,200 kilogram per Kelvin. You might see it that way. So either of the two, we are still correct. The only thing that changes there is the unit. So this implies that it takes 4.2 joules of energy to raise 1 gram of water by 1 degree Celsius, and the formula can be presented as Q equals to mc delta theta. Change in theta, change in T. So if you see change in T or change in theta, we are talking about the temperature, the change in temperature. So from the initial temperature to the final temperature, that is the change in temperature. You know that if you have a water at room temperature, you might be having the initial temperature of that water to be like 35-36 degrees Celsius. So by the time you apply it, by the time you start boiling that water, the temperature will increase to 40, 50, 60 until you get to the boiling point of water, which is 100 degrees. So at that instance, your initial temperature of that water is around 35 or 36, let's say 36.5 degree now, or let's say 35.6 degree to be your initial temperature of the water. So by the time it reaches the boiling point of 100, the final temperature will now be 100 degrees Celsius. So if you need to get the change in temperature at that instance, you just do 100 degrees Celsius minus the 35.6 degrees, which was the initial temperature of that water. You cannot have your initial temperature of water to be 0 because it is water at room temperature, and temperature at the normal body temperature is around 35, 36. So water at that temperature will be around that 34 varying to 36 degrees Celsius. So that is where we have the change in temperature there. So Q equals to MC delta T, which is the delta theta, which is change in temperature, where our Q is the heat energy, the M is the mass of that particular material, the C is the specific heat capacity, while the delta theta is the change in temperature. You can see me saying delta T and delta theta. From the formula, I use delta T. I wanted you to be clear that what I am trying to talk about there is the temperature. So you can as well see it as delta theta, the way I wrote it down here, the last thing where I wrote change in temperature. You might see it as either delta theta, like where I wrote it to be equal to change the temperature, or as it is in the formula. So either of the two, we are still talking about the change in temperature. Then I said that in this particular experiment, electrical energy is supplied to a heating coil, which is placed in an insulated calorimeter containing some water. What does this statement mean? It means that you will have an heating coil inside a copper calorimeter container, which will be plugged to an electrical source. It's just like you boiling water with your boiling ring, but this instance we are not using a boiling ring, we are using a calorimeter. A calorimeter is just like a container, a container which already contains an heating coil inside, placed inside that insulated calorimeter with water put inside by you. So assuming that no heat is lost, assuming that you cover that container very well and there is no escape of heat from the container, it means that all of the energy, all of that heat energy that you supply to it through the heating process, through the electrical process, through the boiling process, all of the energy is used up by the water and the calorimeter. All that energy is being used to boil the water, to make the calorimeter hot. You understand now? So in this instance, if there is no heat loss, there is no place at the lid of that particular container where the energy is escaping, then it means the energy supplied, it will be equals to the total energy you are supplying to heat, which is MC delta T plus MC for the temperature, where MW and MC are the masses of water and the one of calorimeter are the mass, okay, yes, and is the heat capacity of the material. So it means that the energy that is being supplied there will be equals to MC delta theta plus MC delta theta again. The first MC is for water, the second one is for the calorimeter. So you know we are having calorimeter there and we are also having water there. If you are boiling it, if you are boiling a particular water with a container, you see that water, it will be heated up. The particular container you are using, it will also be heated up. Both of them are being heated up at the same time. So the energy supplied to the calorimeter will be equals to MC M of water times C of water multiplied by the rise in temperature plus M of calorimeter times C of calorimeter multiplied by the rise in temperature for that calorimeter again now. Okay, so it now says where MW and MC are the masses of water and the calorimeter. So take note of this subscript. And CC is the specific heat capacity of the calorimeter material. So if you see CW, that is the specific heat capacity of water. Objective of the experiment is to determine the specific heat capacity of a liquid. You'll be provided with a liquid, It can be water, it can be any other liquid, using electrical heating method. Electrical heating method, I've told you, is just like you, trying to boil water. You are heating the water up. So that is the meaning of that electrical heating method. Now the apparatus. This particular experiment, these are some of the apparatus or the components you should expect to use or be given for use. First one is the calorimeter. The calorimeter container I talked about, it's always an insulated one. Insulated, which means that most of the time it will be difficult for it to escape. Lead means cover, heating coil and stirrer. By the time you are heating up a particular something, if you put your pot on the gas cooker, by the time you light it up, the heat that you are being pass to that particular pot, to that particular water, we start from the water down. So by the time you are heating it up, you are trying to make sure that the temperature in that water is the same throughout the water. That is the essence of you having the stirrer. You stir the water so that you have the same temperature at every particular time. So you have heating coil and stirrer, you have a thermometer, you have power source. That is where you plug you have your electrical source. You have electronic balance for measurement. You need to get the mass of your water, you need to get your mass of the calorimeter, so this is a balance used in getting that. You have your variable resistance, a rheostat here. You have your ammeter, you have your voltmeter, you have a switch, you have a stopwatch, and you have connecting wires. The first procedure here says the first thing to do after collecting all your apparatus or your components is that you weigh the calorimeter to get the mass mcal or mc. You weigh your calorimeter. You have sufficient liquid, up to 2/3 of the calorimeter, to cover the heating coil completely, and weigh again. So by the time you are weighing again now, you are no longer weighing mass of calorimeter, because you have already done that. You are now weighing mass of calorimeter and water, because you have added water to it. So now you are weighing mass of calorimeter and water. By the time you get the mass of calorimeter and water, the calorimeter that has already been filled with water, you can now subtract the mass of calorimeter you have measured before, the first one, from it, so that you will now get the mass of water, and you can also get mass of calorimeter now. So you subtract the values from step 1 and 2 to get the mass of liquid. Okay, sorry for mentioning water. I wanted to say liquid because it might not be water, it might be any other liquid. Check the initial temperature of the liquid. Connect the circuit as shown in the circuit diagram given. Remember, I told you that for every heat and electricity experiment, you'll be given a circuit diagram to follow. The rheostat has a resistance of about 10 ohms and is capable of carrying current of 3 amps. Set the rheostat before putting the key so as to maintain a steady current. Switch on the current for a while and allow the water to heat up slightly above 30 degrees Celsius. Afterward, switch off the current. Stir the liquid well to attain a steady value. Take the initial temperature Theta1 as 30 degrees. So it means that by the time you are starting your experiment, your liquid must be at 30 degrees Celsius. It must be at 30 degrees Celsius, and that is why it is being said that you might need to heat it up a little to attain a temperature of 30 degrees if it is not there, depending on the temperature at that moment. So let's continue. Switch on the current at the same time. Start the stop clock. Stirring continuously and keeping the current constant by adjusting the rheostat. Take the readings Then you take the readings of the temperature every minute until the temperature of the liquid has risen to about 10 degrees Celsius but not higher. So if the temperature is has risen by 10 degrees, so it means you'll be having around 40 degrees Celsius now, because we started with an initial temperature of 30. You must note the time. Note the time that the temperature increase occur when it happens. Then you switch off the current, but do not stop the clock, and continue to read the temperature every minute for a further time. Now this is an example of your setup of your circuit diagram. This is a typical example of how the circuit diagram looks like. That box is just that big box, the one inside, that is your calorimeter. That's your insulated calorimeter, and you have your heating coil inside it. You have the liquid, the one dash dash dash, that is the liquid. You can see that it is filled up to the like 2/3 of that calorimeter, and you are having a thermometer put inside. The thermometer is an instrument for checking our temperature, so it will be used to check the temperature of the water at every 1 minute. Now you can see the stirrer. You can use it to stir the water so that you have the same temperature at every point in time. Then down here, down, you have the key. That's your switch. You have your switch. By the time you close it, current will flow. By the time you open it, that means you do no longer want current to flow. Then you have up on top of the calorimeter, you have your voltmeter, and below it, where you have A, you have your ammeter, and there is the power supply is beside your ammeter. So that is a typical circuit diagram that you should expect. I didn't say this is the exact one, but this is a typical example of how it is most likely to look like. Data and result presentation. So I told you the first thing you take note of is the mass of your calorimeter. You might have stirrer inside and you might not. Then you now add liquid. By the time you add liquid, you're having another mass. So by the time you subtract the two, you can now get your mass of your liquid. Then you take note of the initial temperature for that liquid. You take note of the final temperature of the liquid. It is. By the time you are trying to get the rising temperature, you subtract. That's the final minus initial. Your ammeter reading, your voltmeter reading, the heating time. That's why you have stopwatch. That's what the heating time is, for your stopwatch. Then the exercise they're expected to do is to plot graph. For all our experiments, we're expected to plot graph, at least a graph. So for this particular experiment, we have to plot a graph of values of temperature against time. So you see, the exercises to do in your physical class depends on what you will be given in your manual. The exercises to do in your physical class depends on what you have in your manual. So please, just like we did in our physics 107, physics 108 also have practical manual. So by the time and just like we did last semester, please, let's prepare our mind and get in touch with our course rep to do the needful. So from the graph, you read the following: the highest temperature attained by the liquid, the time taken to reach that highest temperature. Then you determine the specific heat capacity of liquid by using the formula heat supplied equals to heat gained by calorimeter and liquid. Heat supply equals to heat gained by calorimeter and liquid. So heat gained by calorimeter and liquid, I've said it before. If you check the slides before now, I said heat gained by calorimeter of liquid, heat gained by the calorimeter and liquid equals to MC, change in temperature for calorimeter, plus MC, change in temperature of the liquid. You had the two for the calorimeter and the liquid together, and you equate it to the heat supply. The heat supply says IVT equals to MC delta theta for calorimeter plus MC delta theta for liquid. So I think that is that. Okay, now this one is saying that Heat gained by the calorimeter and liquid. Okay, that means combined, when both are combined together. So any which way, whatever we are being given when we come for the physical class, depend is what we'll be working with. So you get more knowledge when you come for the experimental class. Now, just like I said in the previous session of this particular class in experiment 2, when I was telling us how to present our precautions, I said use it in, you know, use it in a reported format, use a reported speech. And that is why I'm using this particular format here now, so that you understand better what I meant for in that class. I ensured that the heating element is covered with water to avoid any loss of heat energy. I ensured that the calorimeter is well insulated to avoid loss of heat energy. I ensured that the water was stirred throughout the experiment to ensure that the thermometer reading reflect the heat supply. Now, you see this particular, I ensure that I stir continuously throughout. It's possible. We will do it because, in a that is one of the importance of having group. When you are 5 in a group, designate one or two work for all of you in the group, your group members. While somebody is steering, somebody will make use of the stopwatch, somebody will be looking at the voltmeter, somebody will be looking at the ammeter, somebody will be looking at the thermometer. Everybody must work. That is why it is a group work. It is not just for someone. It's not a singular work. It's for the group. So I have avoided zero error in reading both the voltmeter and ammeter. I avoided error, this parallax, in reading the thermometer. I ensured tight connections. So please, let's take note of all these our precautions. They have, for every experiment there must be precautions. If you say you don't, I don't take note of any precaution, it means you didn't perform the experiment, you didn't do anything. That's what it means. So I want us all to please do the needful. Let's try to get the knowledge. Let's try to understand all these experiments before we come to the lab, so that by the time we come for our experimental classes, it makes our work easier. All these things we are doing now is just to make your coming very easy. You won't have to start struggling with so what will now happen when this one now do this one. No, you will not. You will have that knowledge, that background knowledge of the experiment you want to take. You will ask questions. We will also explain better. We will also put you through, but at least have that knowledge, a little of it before coming. Thank you very much, and have a lovely day ahead. Bye.